In this section, I want to talk a little bit about drag. So drag is the resistive force exerted on an object by some fluid. And so a lot of times when we hear fluid, we think of just water. And certainly water is a fluid. Anything that flows is a fluid. And so that would include water, certainly, but also air. So air is also a fluid. And so when we talk about the drag force, we're talking about the resistive force that any fluid exerts on an object. And so you've felt the drag force before. If you've ever been driving down the road and you stuck your hand out the window, then you are feeling the drag force. So your car experiences a drag force driving through the air. Certainly a boat experiences a drag force, both from the air it's moving through and from the water it's moving through. Now, the drag force actually can take on a couple of different faces. It's actually a very difficult force to model. And so, like we do with a lot of things in this class, we're going to kind of simplify or narrow the scope of what we're going to talk about regarding drag. It turns out that drag behaves very differently in different circumstances. If you've got something like an airplane moving at high speed through a fairly through a fluid that's not very dense, air, right? So you've got an airplane moving through very quickly through a fluid that is not very dense, and it's a pretty aerodynamic shape. In that case, drag behaves in one way, compared with, say, drag acting on like a paramecium or some tiny little object moving through a fluid, right? So in those two circumstances, drag varies greatly. And there's a number we can use to characterize which sort of realm we're in. And it's called the Reynolds number. And low Reynolds numbers apply to those small objects moving through more viscous, denser fluid. Whereas a high Reynolds number would apply to things like that airplane moving through air. And in this case, we're just going to focus on the high Reynolds number situation. In that case, so we're talking about, regular size objects moving through air, pretty much, right? This is a good model for that situation. And I'm not going to ask you questions that attempt to sort of differentiate between those two realms. If I'm asking you about drag, we can assume that we're in a high Reynolds number regime. So, we have this equation then. This is the drag force, and since it's a force, it's a vector, and it includes a magnitude and a direction. The direction is always exactly opposite the motion, so it always exactly opposes the motion. What does the magnitude of the drag force depend on? Well, the 1/2, this is 1/2. C sub d, that is a constant, and it describes how aerodynamic the object is. So a low C sub d would mean a very streamlined, very aerodynamic object, a fighter jet. A high C sub d would be a not very streamlined object, a piece of paper. But C sub d is a number between 0 and 1. For a ball falling through air, that number is about 1/2. Okay, so there will be problems where I don't give you C sub d. When in doubt, just plug in 1/2 for C sub d. It's a pretty good average. So C sub d is a pretty good average. Oh, and here, look, I have a slide where we say everything here. So for a typical object, we're going to plug in 0.5. Rho is the density of the gas or liquid. Again, unless I tell you specifically otherwise, we're going to use the standard value of the density of air, 1.29 kilograms per meter cubed. Of course, the density of air depends on air pressure, relative humidity, all kinds of things, right? So this is just sort of an average value. Again, if I haven't told you something different, go ahead and use this value for rho. A is the object's cross-sectional area when facing into the wind. And so basically, it's like if you were to cut the object in half, perpendicular to the direction of motion, what shape would you see? So if this ball is flying towards you, well, what shape do we see there? That's a circle, right? So the cross-sectional area for this ball is a circle. And no matter what direction this ball goes in, the cross-sectional area is still a circle. If instead I was dropping something like this soda can, well, then what is our cross-sectional area? Well, it depends what direction it's moving, right? So if the soda can was moving towards you, what shape would we use for our cross-sectional area? Well, that's a rectangular shape, right? So our cross-sectional area, if it was moving in this direction, would be a rectangle. The cross-sectional area, however, if it was moving in this direction, would be a circle. So sometimes it depends on what direction the object is moving. And then, of course, v squared. So drag depends on the square of the speed. And so this is really important, right? This is why going a little bit faster in your car causes you to have quite a lot worse gas mileage. Because going twice as fast requires 4 times as much force and 8 times as much power output. So, again, in these high Reynolds number regimes, the drag is proportional to the square of the velocity. So it builds up quite quickly. Thinking about that cross-sectional area again, for a shape like a ball, it's fairly straightforward. So here we see that like I just said, the cross-sectional area of a sphere is a circle, and what's the area of a circle? Of course, it's pi r squared. Now, for a more complicated shape, like say the cyclist, well, we need to approximate that with some simple shape. And so we might say, well, I don't have an equation for the area of a cyclist here. Let's go ahead and approximate it as a rectangle. Here's the width, here's the height. We'll call this a rectangle with an area A. Okay, great. So in some cases we may have to approximate things. But that is, again, the idea behind this letter here, the cross-sectional area. Terminal speed. So if I was to drop this ball, this is a Nerf soccer ball. If I was to drop this, it wouldn't really take it that long before it was going about as fast as it could go. Because it's not that heavy, and as it falls, of course, since air resistance is proportional to the square of the velocity, the faster it goes, the greater the magnitude of the drag force. At some point, as it falls, then, the weight remains constant, the drag force increases as the velocity increases. So here is this, I've just dropped the ball, let's say, the weight is pulling down, the drag force is small, therefore it's accelerating in the negative direction. After some period of time, this drag force has increased, right? Because again, drag is proportional to the square of the velocity. So this drag force has now increased, the acceleration has gone down, the velocity has gone up. At some point, it's going fast enough that the drag force is equal to the weight. At that point, it's no longer accelerating, which means this is the fastest it will go. We call that the terminal speed. Sometimes you'll hear it referred to as the terminal velocity. The terminal velocity, then, is the fastest this object will go if I'm dropping it through some fluid. Let's do a quick example. A 75 kilogram skydiver can be modeled as a rectangular box with dimensions 20 centimeters by 40 centimeters by 1.8 meters. What is his terminal speed if he falls feet first? Okay, terminal speed if he falls feet first. Let's approach this like a force problem. So, if we're going to approach this like a force problem, then we should first draw ourselves a picture. Well, I don't know. He's falling like this. Well, we're supposed to model it like a box. Maybe we should do that instead. Let's see. So here's our box. There we go. Maybe I like that picture better. Let's go with that. There's our box, aka skydiver. He's going to have dimensions of 20 by 40 by 1.8 meters. So this direction here then is going to be our 1.8 meters. With this right here being our 20 centimeters, and this right here being our 40 centimeters. And so, which section faces into the wind? Well, that would be this right here, wouldn't it? So this right here would be our cross-sectional area we'd be looking for. Okay. So let's label that here. Okay. So there's our picture. I like that picture. What else should we do? We should define a coordinate system, right? No reason not to use a standard coordinate system. What's our free body diagram look like for our skydiver? Well, we have the weight force down and the drag force up. If he is at terminal speed, then F net equals 0. Great. Our next step in our force problems is to apply the sum of the forces in the y direction equals ma. In this case, he's not accelerating, So the net force is 0. How do I know he's not accelerating? Because I'm looking for his terminal speed. And terminal speed happens when the skydiver has stopped accelerating. If he was still accelerating, he's not going at his terminal speed yet. So our acceleration is 0. That means this is a dynamic equilibrium problem. We have a positive drag, a negative weight. Again, we should always be looking at our free body diagram in order to create our Newton's second law equation. Remember, Newton's second law is a recipe. It tells us how to create the equation we're going to solve for what we're looking for. It isn't itself the equation we're going to solve for what we're looking for. Okay, and so now we could plug in here. 1/2 c sub d rho a v squared minus mg equals 0. We're solving for v, so we can just algebraify this a little bit. We have v equals the square root of mg divided by 1/2 c sub d rho a. And so really, at this point, we can just plug in our numbers. Our mass, it says it is a 75 kilogram skydiver. G is positive 9.8 meters per second squared. 1/2 is 1/2. Ooh, they didn't tell us what C sub D is, did they? What should we use? 1/2. When in doubt, we use 1/2. Rho, they didn't tell us what that was either. When in doubt, we use that value I gave on the previous slide, 1.29 kilograms per meters cubed. Cross-sectional area, that would be the area of this little rectangle down here. So what is that cross-sectional area? Well, it would be 20 centimeters times 40 centimeters. So we're not even going to use the 1.8. Again, the cross-sectional area is the area that's sort of facing the wind. If this is falling in this direction, it's that rectangle on bottom that's facing the wind. So this should be 0.2 meters times 0.4 meters. Square root of all of that business. And now we run our calculator and we get, and let's see, I'll jump up here. We get V equals 169 meters per second. That is about 380 miles an hour. Okay. Is that a reasonable number? About 400 miles an hour? Yeah, I think so. I think so. A few years ago, old Baumgartner, I think was his name, jumped out of the hot air balloon. They did this Red Bull jump, right? Sponsored by Red Bull. And he jumped out of a hot air balloon at like 100,000 feet. He got going pushing 1,000 miles an hour. But that was up high where the density of the air was actually much less. He was also wearing himself a fancy suit, so he probably had a C sub D of less than 1/2. At any rate, I think this is a pretty reasonable number for this problem.